right, so it's a pleasure to have Matthew Chantry here speaking about weather forecasting with ML, an incredibly prescient topic right now, and there's been a number of very exciting developments recently. Looking forward to the talk.
Thank you. Yeah, so I hope you've all got the balance right of caffeine, carbs and sugar to restart the afternoon. So I'm going to be very much representing a group of people at ECMWF, and my first job will be to explain what ECMWF stands for, because let's do a show of hands, see who's awake. Who's heard of ECMWF before? Okay, slightly higher than my anticipation, which could be about 2 to 3, so that's good. So we're still, for everyone else, talk about that. So the European Centre for Medium Range Weather Forecasts was founded 50 years ago this year, and the idea being we want to go out and do sort of medium range forecasts. What does that mean? Sort of 1 to 2 weeks out. And that at the time was very much viewed as being something where you needed a big supercomputer and lots of smart people to think about how you frame the fluid dynamic equations and all the other parts of the Earth system into something that could reliably make a forecast, and we'll talk about that reliability later, out between 1 and 2 weeks. And so a whole load of nations across Europe got together. They pooled money to establish a centre. It used to be only based in Reading. Now it's based in a few centres across Europe. And the idea is we are fairly unseen across Europe. We provide data, services, other things to the national meteorological organisations, who are really the fronts to people, to businesses, to organisations around there. So we're trying to sort of push the frontier of the skill of particularly medium range, although we're also interested in even longer time scales, so out month to seasonal, even to decadal time scales. And so I think, first of all, I'm going to spend a few minutes talking about how weather forecasting has been done for a lot of those 50 years, so that you have the context of what it means for machine learning, what role there is for machine learning. And so I talk about the process of our sort of integrated forecasting system, which is the name, the IFS is the name of our physics-based system. And it has a few different steps in this sort of weather forecasting chain. At a national meteorological organisation, this is even more complex because there's a whole load of stuff at the end to do with getting into products and use cases and more connecting to the users. That's not our job because we provide more raw data to those national centres. So this starts with the process of data assimilation, so multiple times per day. We gather a huge range of observations, about 800 million, that come in through the doors every day, of a variety of different sorts, from on the ground to up in space. And they help us form a complete state of the Earth system as an initial condition, or series of initial conditions. That process involves optimization of finding the best physical model state that gets close to those observations. And then what we do is we run that initial condition out forwards in time, out to 10, 15 days, to make a prediction or a series of predictions into what the weather is going to be like. So this process of data assimilation involves a huge set of observations, as I give a sort of sneak, oh, it's going backwards, that's fun. A sneak peek of here, oh no, it went forwards instead. Sorry about that. But you don't need to sort of really take that all in, except just to realize the complexity of the scenario that we're talking about happening on a daily basis. So once that's coming into initial condition, we then want to go away and do the forward modelling. And nowadays what that means is the representation of a very large number of Earth system processes, all in one unified Fortran model that runs on a fairly sizable high-performance computing system now based in Bologna. So that means resolving sort of the atmospheric dynamics, trying to capture unresolved turbulence, understand ocean, sea ice dynamics, the impacts of waves, both for forecasting waves and also for that stress that happens to impact near surface winds. And so you're aiming to build a model that has captured all of this phenomena all in one go. People maybe don't appreciate it, but weather prediction has been getting steadily better over time, but at such a rate that it's sort of quite hard to see on a day-to-day basis. So this is an overly complicated plot, basically showing how skillful we are at a variety of different lead times. So 100% would be perfectly skillful, so that's just off the top. And this is looking at how skillful we are at day 3, day 5, day 7 and day 10. And this is the skill as measured in that year of the forecast. And you can see that as time has gone on, this has gone up. And in fact, if you look at what's happened sort of in a decade or so, which is illustrated here, you can see that the equivalent skill we used to have in, say, day 3 is now the skill that we have in 5 days. So we sort of moved that window of opportunity, that ability we have to make forecasts by 1 to 2 days in every decade. And that's come from a huge, yes?
Two quick questions. It looks like in the last 5 years, progress hasn't been nearly as good as it was in the 5 years before that. Is that a correct understanding?
Yes, although one of the challenges with this plot is it's sort of also underlying is the variability in the Earth system, insofar as some years are just easier or harder to predict than others. So you have to take these variations. That doesn't mean when there's a dip that we actually got worse at modelling. It means that for whatever Earth system scenario we were in, it was actually harder to model that year. You could maybe argue that performance is beginning to stall, yes, particularly as you're sort of asymptoting towards 100 for some of these times. But I think as you can also see that the progress further out, I'm not doing very good at this. I keep expecting the cursor to make sense. At day 10, that skill has been fairly substantial sort of there. So it's harder and harder to improve the short term, easier, but still possible to improve the large scale. And this has been dubbed the sort of quiet revolution in weather forecasting, and has come from a huge set of different sort of contributions. But one of the key ones, someone insightfully asked me about this, was Moore's law during the lunch break. So that's this idea that computers have just gotten faster, and so we've been able to solve the equations more quickly or at a higher spatial resolution every year upon year. So we buy a new computer, it's just a lot more powerful, and that's sort of going away, or at least transforming into different computational architectures. So it's getting harder and harder to realize these gains year on year. The other thing that I've not touched upon before is the butterfly effect, the fact that we're dealing with a chaotic system, the fact that even if we had a perfect model, that we don't, with an imperfect estimate of the initial state, that will eventually propagate from the sort of metaphorical butterfly wings up to the idea of being that your tornado, your hurricane, whatever severe event you have, is misplaced if you do this as a single shot forecast. So framing it, actually the scores I showed before was a sort of deterministic forecast. That is a fundamentally flawed way, particularly to do sort of week 1, week 2 forecasting, and something that we've been pioneering over a few decades is this use of uncertain forecasting to get something that is actionable, reliable, etc., etc. So how do we do this? Again, I'm still in physics mode. I will turn to machine learning in a moment, but we need some backstory. We do this with ensemble predictions. So we do this by creating, and you can ask me questions, I'm going to go at a high level for now, an ensemble of different initial conditions, so non-identical, that are trying to capture the uncertainty in just estimating the current state. That is a surprisingly challenging task to do in its own. And then we propagate that forwards with a series. We happen to do 50 members of that ensemble forwards in time to then deliver a sort of cone of uncertainty and estimation of that uncertainty. And the joys of doing that as an ensemble approach is you get a good estimation and get some information on the sort of joint distribution, which is actually impactful for a lot of applications. So imagine you're doing energy load forecasting across Europe. You need to know not just where it's going to be sunny, but also the winds that are happening over the North Sea, as we heard about a bit before. And you need to have all of that encapsulated in consistent scenarios to do a good job. And so I'm almost done with my slides on physics. How do physics models deal with these uncertainties? Well, we have to sort of represent uncertainty, or we choose to represent uncertainty in 2 places. So we first are trying to encapsulate the initial condition uncertainty, so building not just one initial condition, but 50 that try and encompass the true state of the Earth system now, and then propagate that through not actually a deterministic model, but a model that has some underlying uncertainty, where we've tried to estimate which parts of our model are accurate and which parts are harder to encapsulate, so that even if we fix the initial condition, we get different answers. And so the combination of those is trying to give some distribution out into the future of what the weather should be like. So an example of this would be tropical cyclones. This is a really boring event. I'm sorry, I should have shown something where the cone was doing something more exciting. And so you can see how this information is being shown or used in terms of if you would go and count 50 plus 1 tracks of different possible tropical cyclone trajectories. Here, the cone is getting wider, although not dramatically. Sometimes you can get some really interesting sort of bifurcations or other sort of very non-Gaussian behavior in, for example, tropical cyclone tracks. And you can also look at this in terms of, this is the probability that the tropical cyclone is going to hit different categories of intensity. And so by looking at these different realizations, these different ensemble members, you get to sort of build up this complex picture that you can then probe for lots of different applications. Because that's the beauty or the challenge of weather forecasting, is it's being used by a large number of users for a large number of different use cases. So the state that we have to predict is highly complex. And that means that the supercomputing power is also big. So to give you an idea, we use about 50 nodes on a supercomputer to just make one of these trajectories. You then multiply that out because you want all 50 to come in at once. You have a significant amount of computing power to provide this ensemble. And we know if we'd run a larger ensemble, I mean, we'd get better information, not dramatically, 50 is a nice sweet spot for that, but we could get even better estimations of the uncertainty. So finally, I'm sorry, it took me how long? A few minutes to get to this, but now we enter machine learning. It's been an interesting and busy few years in the history of machine learning for weather forecast. Back in 2018, we created a data set called ERA 5, which is trying to give you the estimation of what the Earth system looked like for every variable, every place on Earth from, well, now back to 1950 to present day. So it's one perfect contiguous data set. It wasn't designed for machine learning, but it turns out it's extremely good for machine learning. And it's very accessible in terms of it's openly available to download. It's very easy to go away and use. A few years later, not a few minutes later, this inspired a whole load of new organizations who hadn't been involved with weather forecasting. Weather forecasting is a relatively self-contained sort of set of organizations who had the ability to run weather forecasts, to develop weather forecasts, came into the field and said, hey, this looks like an interesting problem. Colleagues of mine had actually posed this, mostly as a sort of research interesting question back in 2018. The skill had been not at all interesting. But what happened into 2022, 2023, etc., is people started to come out with results where they were able to claim that they were as accurate or even more accurate than the state-of-the-art forecasts, which happens at the moment to be us. So there were lots of papers coming out saying we are better than ECMWF at medium-range weather forecasting, which makes you sit up and take note, as it should. And what's more, they were also, I'm going to touch on this in a second, a lot more energy efficient than a physics model. And so this was a very exciting prospect for building large ensembles, for being able to run more regularly forecasts, and for just generally being able to improve the products. And so one of the interesting things to see here is that there's also quite a lot of representation from big tech. I'm sorry to say, I don't think Apple are represented yet, but who found this to be an interesting problem to cut their teeth, and a lot of them have been rewarded with Nature papers, etc., for engaging in this discipline, and have really helped push this envelope forwards. So it took us a little bit of time to do some sort of testing ourselves, check that this was the real deal, but we decided, no, this is going to happen. We think this is going to be a part of how we do weather forecasting. And so we spun up a group to say, right, we're going to make our own operational weather forecasting, not to replace the physics model, but to run alongside it, for there to be two parallel technologies to make weather forecasts, and we're going to let the world as a unit decide what is suitable for which purpose. And so that's the journey we've been on, and I'm going to talk to you about how we do it, first of all from a deterministic perspective, but also then start to touch eventually on the title of the event and talk about how we deal with uncertainty, because that's of interest to you. So what we're going to go back to is the chain, and I'm going to talk about the fact that right now, in the context of this talk, I'm going to forget about the process of data assimilation and building initial conditions. This is a really interesting problem. It's outside of scope for the talk. It's also less developed so far in the world of machine learning. It's still likely that machine learning is going to have a big impact here, and this is still an extremely expensive part of the forecasting chain. So to give you an idea, for a physics-based model, we spend about the same amount of computation building the initial condition now as we do making that forecast out into the future. So about 1 hour in our time to build that, and about the same amount of computer, and then another hour to go away and make that forecast. So what we're doing here is just seeing to replace this modeling step. To sort of cut a long story short, here is a snapshot of the quiet revolution as I showed before. I've cut it off a bit more recently, so the lines look particularly flat in this instance. And we have injected on top some of our own now machine learning forecasts. And you can see that's these new dotted lines that have appeared here, that at all lead times, this is a significant step forward. It's not perfect forecasting. That's extremely hard to do. But relative to the amount of time it would have taken you, the amount of investment in HPCs, in developing better algorithms for physics models, this is a significant step forward, probably in line with something like a decade's worth of R&D into physics-based modeling. So this sort of acts as, well, there's a new revolution in town. It's very much not quiet, and is based around machine learning. So how does this work? How are these problems framed? I'm going to talk about what we're doing in terms of the AIFS, which is our sort of homage to the integrated forecasting system with the artificial intelligence forecasting system. A lot of the design choices here, there are some parallels or equivalents that are happening in this wider scientific literature I talked about, but it's easier for me just to delve into the details of how one of them is working. The idea is as follows. You would start with the state of the atmosphere at a certain time t, perhaps a series of those over some recent time, so time t maybe a few hours in the past. To give you an idea of the amount of parameters that you have there, this is a grid with maybe 500,000 grid points across the world, so that corresponds to about 30-kilometer resolution, and you have about 100 different parameters that you're measuring at every point in space. So a sample, in terms of the machine learning framing, has about 50 million floating points. So this is big compared to even a large language model with quite a large context window. However, it's still very small at the moment from the dimensionality of the solution you're building. Part of that's the design. So we're building a graph-based neural network. So this has, therefore, a lot of shared weights. And the idea is you would use an encoder to map to a hidden grid where you do the computations in some latent representation that you have no idea how it corresponds to physics. You would then allow that to run on some processor, again, passing information on some grid to move that and then decode that back out into a future state of the atmosphere 6 hours into the future. And what you do is you design this such that the things I'm still struggling with that, I'm so sorry. I keep wanting the pointer to be the top button. I will learn one day. You design it so that the things you're predicting, your state out, is basically the same as your state in, so that you have something that can then run auto-regressively. So how you train this is a supervised training process. So you pre-train it to say, I want to step forward one step into the future as a 6-hour forecast. And then you then actually, within the sort of gradient loop, you're then going to apply the model many times to learn how that forecast should evolve over a few days. So this is, in our scenario, 12 steps out, and then back propagate through multiple copies of the same model to figure out a model that's capable of building you a consistent trajectory over a long lead time. And we are minimizing here just an area-weighted mean squared error, so a simple deterministic metric, which those of you that are on the ball will tell you, will be able to predict that that's going to give you the sort of best estimate, but not any representation of uncertainty for the processes that are underlying. The uncertainty of the fact that you're dealing with a chaotic system, even if you knew, still not there, Matthew, what the state of the art is now, you would not, even with perfect knowledge of the state, you would struggle to get a perfect prediction 6 hours into the future. So just to give you some scale to connect back to the numbers I talked about earlier, so this training data set that was not built for machine learning, it was actually built for understanding and measuring our climate, past and into current, cost by our measure of units on our supercomputer, about 15 billion, so a significant part of our supercomputer running for many years to build this. In this equivalent sort of unitless quantity, making a single forecast costs about 200,000. The energy costs for making one of these machine learning forecasts are many orders of magnitude cheaper. You are down to using basically a single GPU for 2 minutes rather than 50 nodes for the best part of an hour. So you have this dramatic energy, dramatic HPC reduction that's come in. Training is not particularly cheap, but still actually is relatively small compared to the costs of running these physics-based models. So uncertainty quantification. Let's finally get onto it. So this was my sort of diagram before. How do physical models deal with uncertainties? We now want to map this onto, I had a scenario before, we trained a model, we trained it to minimize the mean squared error. What we get there is a very good single guess of what the forecast is going to be in the future. It doesn't tell us anything about what the uncertainty is going to be about that future state. It doesn't give us an ensemble of different equally plausible scenarios. So here what we want to do, well, we can actually rely still on the initial condition mechanism that we do. I told you we're skipping that step for now. We're going to benefit from our representation of initial condition uncertainty that the physics model uses. And so what we need to do is we need to train a model to be uncertain, to find a way of framing the problem such that the model has a fair representation of its own uncertainty. And so what this means really is enter generative machine learning. And so I'm going to talk to you briefly about a couple of different approaches that are happening in the field and that really show that this is quite an exciting field to be part of. There's lots more research to do, and I frame this more as open-ended rather than very much closed sort of problem. So the first work I'm going to talk about actually didn't happen at ECMWF. This happened at Google DeepMind, where they applied fairly standard sort of image-based diffusion technology, so the Karras et al. Paper, which came from NVIDIA, to the problem of weather forecasting. So what does this mean? This means breaking down the idea of predicting the next state into a series of steps where you're trying to remove noise from that state. So here is the time increment that you're trying to get. Here's how the winds are changing between one time step and the other in the future. So the model is learning to start from a pure noise scenario and iteratively remove that to give you one possible scenario of what the winds might look like in the next step. And so diffusion, for those of you who are sort of practitioners of it, comes with some nice sort of underlying mathematics that tell us that what it should be doing is really, when you run a particular sample, is sampling from the possible distribution of future states that are consistent with the state that you have presently. And so this gives you a method of moving the atmosphere forward in time. What it does, interestingly, is introduce a new dimensionality for iteration. So we talked already, the way you get to a few days out with the first generation of weather forecasting models is you apply the model autoregressively to itself. Here you actually have two iterations of that applying sort of autoregressively, because you first work down in terms of, to make a single step forward, you continually remove noise. And then finally, you have a nice, smooth or coherent state to then move to the next step and apply this process again. So it does moderately significantly increase the computational expense, and it also stops you at the moment doing this idea of auto-regressively training. So if we go back a few steps, one of actually the nice things that got these models to be skillful is minimizing not just the error over a single step, but the error over multiple steps. But this did provide, I don't have scores for it here, just in the interest of time and space, very competitive forecasts that were outperforming, measured from a probabilistic perspective, our state-of-the-art physics-based ensemble method. The second method is to go about and directly optimize a probabilistic skill score. So here what we're going to do is not just run through one sample, but duplicate the initial condition a few times. So duplicate the state of the atmosphere a few times. And for each of those samples, perhaps run on different GPUs, we're going to give it different ideas of random noise to help steer, to help learn a representation of model uncertainty. We're then going to apply our model to make different forecasts of the future. And then we're going to use a proper skill score that's going to reward you for capturing the truth within that ensemble of predictions. So the continuous rank probability score, for those of you who sort of haven't come across it before, is this idea of it can be viewed in sort of two different formulations, either sort of looking at it from a CDF perspective. You're looking to try and get your distribution predicted from your model as close as possible to the delta function that is, this is the true value for your y. Framed in another perspective, you can think about this from a discrete formulation. You're trying to get your ensemble members all close to the true value and not too far away from one another. So this metric is rewarding you when you make a bold prediction and get the answer right. You get the truth in this you get the true value in this, and it's going to penalize you heavily if you don't have the true value in the distribution. So it's going to want to reward you if you are struggling to predict what the future state will be to make your distribution wider. And so it has some very nice underlying properties. And so this is what we do. We adapt the formulation of this sort of auto-regressive training, and we just say we're going to propagate. In fact, you can do this with quite a small ensemble. You can estimate this in a noisy way, just like machine learning is full of noisy estimation, particularly with neural networks. Propagate forward in a small ensemble and try and find one that is directly optimizing this CRPS, directly optimizing this proper skill score over a course of a few days. So what does this mean? So a weather forecast is viewed over very many different variables. And so I could show you a chart with hundreds of different variables and how the skill compares with each of them, but that's a bit of an overload. So here what we just look at is I'm looking at temperature fairly low in the troposphere at various different lead times. So we see that the error is getting worse over time. And this is in fact measuring the CRPS, which is the headline skill score of how we measure the accuracy of probabilistic weather forecasts. And what you can see again is this idea that we've really still not learned how to use a laser pointer, but we've really moved this envelope forward. So the dotted green line is the physics-based model. The blue line is the machine learning model, this one that optimizes the CRPS, and we pushed forwards the forecast accuracy by something like 12 to 24 hours in advance. So we've pushed forward this window where we can get equally skillful forecasts out into the future. We could talk about measuring reliability. We have lots of things that we like to look at to try and sort of understand whether these systems are not just doing well in this headline skill score, but being reliable. Two things that we like to look for in the weather forecasting domain are sort of the calibration from a measure of looking at what is the error of the ensemble mean and what is the spread of the ensemble, and those two should be growing in concert with one another, and that's what this plot up here on the left is showing. So you can see there's two lines. One of them is showing how spread the ensemble is, one of them showing the root mean squared error of the mean of that ensemble prediction, and these two are fairly lockstep over this course of 15 days, with the fact that it's actually over dispersive, so it's underconfident for the middle few days. Framed a different way, we can look at sort of ranked histograms and see where the truth is going to lie in our ensemble. So we would like it to lie equally frequently at every point in the ensemble. So we'd like the line to be perfectly horizontal. We see that physics models struggle with this. So this is looking at temperature in the atmosphere, and we see the red line is one that is U-shaped. So this is an overconfident model. You are more likely than you'd like to be for the true value to lie outside of your distribution. And these are a few different versions of machine learning models. So a diffusion-based one and a score-optimized based one. And you can see that they're doing a better job, still not a perfect job, of getting a flat rank histogram, so a better calibration of the model. There's still a lot of work to do in flattening this line perfectly, but they are not very overconfident. So this is now an operational technology, at least by our definition. So we run this 4 times a day. You can go to our website and see forecasts that are made using machine learning. And here what I did is I looked at 2 different times and said, how well are we doing for this mini heat wave we've been having, at least in Cambridge for the last few days. So this is a forecast initialized from the 3rd of August, so quite a long time ago, showing the weather that it's going to be like going into yesterday and today. I actually forgot to look up what value we hit yesterday and today, but it was certainly around 30 degrees, I think just under. And you can see that the distribution, so the box and whisker plot is quite wide, so the uncertainty is quite large, but 30 degrees is sort of towards the end, but still within the distribution. And if we look to the forecast from closer to now, so if we look to the forecast initialized midday on Sunday, you can see that the distribution has shrunk a lot. We're a lot closer to the right time. We've got that better. The distribution has warmed a bit, and the signal has come out even more clearly. So I think this one, from a reliability perspective, would score well. It's not just me eyeballing charts that decide if a system is reliable, I should note. We do a lot of verification, and you can ask me questions about that. We've also been making our models open source so that people can play with them and explore them for ourselves. So this is uploaded on Hugging Face, and we show how you can actually run this from a real initial condition. If you have a sufficiently modern GPU, you can go away and run that, see how it performs for yourself, try and break it, and we can learn interesting things from breaking it. And so I can't remember if that 5 minutes is including a question time, but we'll see. My summary and my open questions is sort of uncertain machine learning is being actively used now in operational weather forecasting. I've talked about what's happening from ECMWF, but in fact, I could have also given a lecture about how we're working with a lot of the national centres who are really looking to use this technology themselves. It will be coming to apps near you very soon. It will be coming alongside physics-based system to decision-making soon. It's exciting because it allows us to push forward the frontier of skill and also offer larger ensembles for a fraction of the cost. And so that can allow you to sort of better estimate the tails of possible rare events or sort of get better indication earlier of when really dangerous weather is going to come. But this is really, I think, a lovely field to be in at the moment because I've shown you some results, but it's definitely not a closed book. So we've seen 2 different methodologies for probabilistic forecasting. What I think is interesting is this sort of direct skill score optimization is leading the way right now. But it's interesting because this is an approach that sort of is happening in weather, but is running sort of contrary to a lot of the other domain in sort of video image technology, where diffusion is the be-all and end-all of the technology space. And so I think the interesting thing is, as we learn more, I mean, we're already aiming to learn from this video image space, understanding why we have a different approach emerging as possibly the more powerful approach. There's a lot more to do. For example, the CRPS you might have noted is like a pointwise estimate. It doesn't look at the joint distribution across variables. It doesn't look at the joint distribution across space. Those appear to come out quite well out of the box. And one of the explanations I've had for that is that you're using a graph neural network that's basically sharing weights. It's sharing the way to do predictions over the globe anyway. So it's very hard to make something that's optimizes the skill score locally, but ensemble members aren't coherent with one another. But there are really interesting things to look at there. And then also just sort of this idea of we want to have larger ensembles to do a better idea of tail events, representation of extreme events. We don't have the data really yet to understand how well we're doing on those, how much we need to really tweak the algorithms to get a better job of doing this. I think that's it. Questions? Great question. We see running sort of multiple years away from the training data that these models remain skillful. So it's not like you've trained a model of the day where you need to be retraining, like actively learning sort of on yesterday's data. That might really make you the best possible forecast, but as you do that, you're eating into your validation and testing data. And so at the moment, we take quite a cautious approach of having 1, 2, 3 years of independent data of the most recent data, knowing that we hurt skill a bit there, but that we have really trustworthy answers on that. I talked about the fact that this sits on top of the physics-based model for making initial conditions. That physics model is iterating year on year, and the distribution of the data is evolving. So that's actually the leading reason to retrain these models at the moment, is the underlying data is shifting, it's not static. And then there's a climate change angle as well. But that one is very slow moving, and so it does not appear to be so, for now, does not appear to be so problematic.
Yeah, thanks a lot. So a few slides ago, you were adding some noise.
Yeah.
Which sounds really difficult because there could be lots of ways that the noise should be added.
Yeah.
So I guess you have an extra model there.
So the noise is injected, there's a few different ways of doing it, either doing in sort of like conditional layer norms, if you're familiar with those as sort of building blocks of neural networks, or actually just as extra like input fields to the model. So the model has all the many layers in a neural network to learn how to shape that noise. And it seems like broadly the exact choices you make in your noise in terms of like Gaussianity, if there's correlations in time or space, they're not the leading, they're not a leading problem. So there may be things in terms of fully optimizing this technology to figure out what the optimal sort of noise looks like for the model to learn to shape. But the model has a lot of non-linearity to basically take Gaussian white noise and shape it into a very non-Gaussian representation of uncertainty.
So are your forecasts resolution dependent, or have you looked into architectures like ECMWF to consider resolution?
So there's one of the papers sort of uses neural by NVIDIA uses sort of neural operators. So as a way where the claim is that they will be more resolution dependent, like to train at maybe one spatial resolution and apply it another. I would argue that's more of a claim at the moment than a reality. The graph neural networks are also fairly independent to resolution. We're starting to do some testing in what happens if you train on data with one spatial resolution and then apply it to data with another spatial resolution. Or actually, we have a hierarchy of different data at different resolutions. So it might not be zero shot running on data with a different resolution, but saying we have this massive trove of relatively coarse data and then this small trove of relatively high resolution data. And so methodologies that can learn from both of those data sets and then apply at as high a resolution as possible. Because that is actually one of the caveats to these machine learning models at the moment. They are competitive when measured for real events on their skill, but they don't have at the moment the spatial resolution of this. So our physics-based model can operate at 9 kilometers globally, and the machine learning model operates at 30. We'll have that done in a few years.
All right, let's thank the speaker again.